Okay, so it's time to start making some other physical measurements here. Start talking about Susilo distances. So the first one, we want to talk about these, definitions, these terms we've already defined before, but just to get out again, astronomical unit being the distance from the sun, Earth to the sun. All right, and on average, because it is an ellipse, all right, and we have a close point and a far point, okay, aphelion, perihelion, all right. 1 AU is equal to 1.5 times 10 to the 11 meters. There we go. So for light year, the distance that light travels in a year. What is that? 9.46 times 10 to the 15th meters. So a while back, in a few videos ago, you heard me define what a parsec, or define a parsec, kind of arbitrarily, just giving the number. So here we're actually going to end up defining it. All right. So the parallax method, the big idea here that you need to be able to explain. All right. So this purple thing here, this is the sun. All right. And then these two blue things, this is the Earth. You could say in January, and then the Earth in July, we'll say. All right. And so between both of these places here, all right, if we're looking at some star, and we're actually comparing against background stars, if the star is close enough, that star will change its position amongst the background stars. Okay. So when viewed from two different positions, it will have displaced relative to that fixed background. What we can do is we can measure that angular displacement, all right, at two different times during the year. And once we've measured that, we can create a triangle because we know the distance from the Earth to the Sun, okay? We know that angle in question, okay? We can just measure that by how we turn our telescope. And then finally, okay, we have both of those pieces of information, create a triangle and determine the distance to that star, all right? So, we'll write this out here. Our official definition of the parallax method, based on this idea of parallax, remember when you look at a meter stick or any sort of instrument at an angle, you're not going to be looking at it, you're not going to be making an accurate measurement because it's not going to be lined up with the object properly, okay? But here, with stars, this is what we do on purpose, okay? The object is viewed from two different positions. It appears displaced against a fixed background. All right? And what we do is we measure the angular displacement at the two times, and from here we determine the distance. And so this is the whole method. All right, using trigonometry. All right, so this is pretty much it. What we can do here, all right, this is another slide here, whoops, is that we know from this little diagram that tan of P, we call it the parallax angle, right, is equal to R all over D, okay? And so, stitch this around, D is equal to R all over tan of P. And remember way back when we were talking about resolution, and actually, diffraction, we had made the small angle approximation. So when we do that, okay, tan of P is approximately equal to P, all right? So, D is equal to R all over P, and we gotta make sure that we end up keeping our parallax angle in radians, because the small angle approximation only works when your angle is in radians. And if you don't remember that derivation, you can go back to that video that talks about diffraction. So this is going to tell us, all right, how far an object is based on its angle. So our official definition now for the parsec actually is going to come up here in a little bit. But before we do that, let me just explain to you. There are multiple measurements now for an angle that we're going to be using, especially since we're going to be looking at things really far away. These angles are going to get really small. So we all know, all right, that one circle has 360 degrees in it. Well, you can take one of these degrees and you can split it into 60 divisions. And when you do that, 1 degree is going to give you 60 what we call arc minutes. And you're going to split that up even further, okay? We use this little single hash for this, and then you split that up even further, and we end up with 60 arc seconds, okay? 60 divisions of 1 arc minute, and that's going to be given with the double hash here, okay? So, yeah, these are your new angular measurements that we're going to be taking here. And here, sorry, we're going to finally define what a parsec is. So what a parsec is, it's the distance, okay, subtended by a parallax angle of 1 arcsecond. So what this gets at is that it is 1 parallax arcsecond, and what we take is the par and the sec from that 1 parsec. Okay? So again, this is just 1 parsec is equal to 1.5 times 10 to the 11 meters, all right, divided by, and it's, again, we have to convert this into radians, so it's 2 pi radians, okay, for all right, every 360 degrees, and this is officially 1/3600th of a degree. Remember, there's 60 arc seconds in an arc minute and 60 arc minutes in a degree. So there are 1 arc second is 3,600, excuse me, degrees. All right. So this is the conversion from degrees into radians for that 1 arc second of angle. When you do that, you end up with a distance that's 3.09 times 10 to the 16th meters, all right? And if we do this conversion, this is approximately, okay, these are all approximate around here, 3.26 light years. All right? So if D is in parsec and P is in arc seconds and R is in astronomical units, as it typically is, okay? So let me write that again, okay? If D is in parsec, all right, P in arc seconds, and R is in astronomical units. We've defined all these things in terms of that. So 1 parsec is literally 1 astronomical unit, all right, over 1 arc second. If all of your units are as such, then the equation that was D equals R all over P, keeping with these units, simply becomes D equals 1 over P, only if we're using these units, okay? So we can make life really easy, keeping distances in parsec and keeping angles in arc seconds, and we can just use this formula to determine how far the object is based on our parallax angle that we measured in arc seconds. Yay! So, let's do a practice problem. We have our parallax angle here for series A. It's 37 arc seconds, so we want to determine the distance to the star in parsec, meters, and light years. So we start out, P is equal to 0.37 arc seconds. D is equal to 1 over P. All right, 1 all over or 0.37 arc seconds here is equal to 2.7 parsec. Okay? So now we want to convert this into meters and light years. We can just do that with the following conversion factors. Alright, there we go. And the number of light years here, or meters, excuse me, 3.09 times 10 to the 16th meters per parsec. Again, quick conversion. There we go. So those are some good practice problems introducing stellar distances and the parallax method. The next few videos are going to talk about apparent and absolute magnitude, as well as spectroscopic parallax and Cepheid variable distance determinations.